Welcome to that lecture online, and by special request we're going to do some more examples on Gauss's law. I remember I only did about 3 examples and some viewers said I'd like to see a few more examples, so here we go. Some more examples about Gauss's law. And Gauss's law is a really nice law to work with in order to find the electric field around a distribution of charge. So what we're going to do here is we're going to assume that we have a conductor material that has charge on it. And typically when you have a conductor material, the charge will reside at the very outside surface of the conductor because the charges want to be as far away from one another as possible. And that can happen when they reside on the very outer surface of the conductor, which means the inside surface will have no charge, just the outside surface. And what we're going to do here is find the electric field strength just outside the region where the conductor resides. All right, how do we do that? Well, Gauss's law is just perfect for that. So here's the equation that describes Gauss's law. It says that the surface integral of the electric field times the dA. Well, dA is a small little area element. If you think about it, just take a small little area called dA, and if you want to make that a vector quantity, then you multiply that times the unit vector perpendicular to that surface. So basically, it would be called unit vector, the n vector, like that. And so we can then write the vector quantity dA is equal to the size of dA, which is simply dA, times the unit vector n. So that's really what that is equal to. So if we now multiply with a dot product the electric field strength times dA, notice with a dot product we know that E dot dA can then be assumed to equal E times dA times the cosine of the angle between them. I'll draw a line there so we don't confuse this here. So in other words, if the direction of E and the perpendicular line to the surface, or the perpendicular vector to the surface, if they're not parallel to each other, there'll be an angle in between, and then we have to multiply the magnitude of E times the magnitude of the direction, the magnitude of dA is simply going to be, of course, the size of dA times the cosine of the angle between them. Usually what we do with Gauss's law, though, is that the angle between the electric field and the perpendicular to the surface is equal to 0. And most likely, if we draw the Gaussian surface correctly, that is usually the case. And so that makes the problem a lot easier. We don't have to worry about the angle between the direction of the electric field and the direction of perpendicular to the surface. All right. What that means then is we can then change this integral. Instead of writing it like this, we can simply say, well, that's equal to E times the area, the total area of the surface in question. And that is then going to equal the charge inside divided by epsilon sub naught. Now, of course, the charge inside in this case will be the charge contained within the Gaussian surface. So what I drew here is I have a conductor material with charge on the outside, and I drew a Gaussian surface, which means I drew kind of a cylindrical shaped imaginary object, so to speak, like a cylinder, where the cylinder protrudes through the conductor. It has a portion of it sticking outside this way, a portion sticking out down below. And so whatever charge is contained within that particular surface, as we call it, that is the charge inside, and we divide it by the epsilon 0. Of course, epsilon is what we call the permittivity of free space, which is equal to 8.85 times 10 to the minus 12 coulombs squared per Newton per meter squared. All right, so now we have to think about how much charge is inside right here. Well, that depends upon the charge density, which is the charge per unit area. Here we're talking about the surface density, not the volume density. And actually, instead of using that letter right there, typically we use the letter sigma, which signifies the surface density of charge. So let's use that symbol instead. Okay, so now we'll be able to calculate this. This is a constant. E field is what we're looking for. Now the area. So the area contained that has where the electric field goes through. And notice the electric field will emanate away perpendicular to the surface, and therefore the area of the Gaussian surface through which the electric field will go is simply the end of that cylinder. So if we draw a little cylinder on the side here, so here's our cylinder. Like so, that's a Gaussian surface here that we drew, and we have the electric field going away from the conductor straight out the cylinder. So the area of the cylinder is simply this portion. This is the portion of the Gaussian surface through which the electric field goes. That's the only portion we're concerned with. And so this would be equal to pi times the radius squared. The radius, of course, being the radius of the circle portion, or the end portion of that cylinder. All right, so now we can write that the electric field times the area, which is the pi r squared, is equal to the Q inside divided by epsilon sub naught. So we'll tack each portion of the equation one by one. So this is what we're looking for, the strength of the electric field. Pi r squared is now the area through which the electric field goes through. We do not have to worry about the bottom part of the surface, or this portion of the area, because there's no electric field going towards the center of the conductor. Remember, there's no charge on the inside surface, so therefore no electric field inside a conductor. This will be equal to 0. We don't have to worry about it. So only about this outside portion right there. Okay, now we still have to find the Q inside my Gaussian surface. It would, of course, be all the charge on the outside of the surface of the conductor. And so we can say that Q then is equal to the area density times the area. So this would be the charge per unit area times the area that gives us charge. So in this case, the charge density, well, I didn't give you a charge density, did I? So why don't I give you a charge density where this is equal to, well, I'll write it over here, get out of the way here. So let's say it's equal to 5 times 10 to the minus 6 coulombs per meter squared. All right, so that would be the charge density on that surface. So now we can plug that in here. And let's say that we want a radius. Let's call the radius r equals to 10 centimeters. All right. So let's plug that in here. So we have sigma, which is 5 times 10 to the minus 6 coulombs per square meter, times the area. And of course, it would be the area of the end of that cylinder, which is pi times the radius squared. In this case, that would be 0.10 meters. And we have to square that. 5e to the 6 minus, there we go, times pi times 0.01 equals, so we have a charge of 1.57 times 10 to the minus 7 coulombs. All right, that will be the charge inside. We have our constant, so therefore we have E is equal to Q inside divided by epsilon sub naught, and then we'll bring the pi r squared over here. Now we plug in all the numbers. So we get 1.57 times 10 to the minus 7 coulombs for the charge inside the Gaussian surface. Epsilon sub naught is 8.85 times 10 to the minus 12. That would be coulomb squared per Newton meter squared. Then we have pi, and the radius, again, 0.10 meters, and that is squared right there. And so let's divide that by 8.85 e to the 12 minus, and then divide that by pi. Let's see, where's my pi? There we go. And divide it by 0.01, and we get, wow, that's quite large, 5.65 times 10 to the 5th times 10 to the 5th, and that would be newtons per coulomb, which would be the appropriate units for the electric field. And of course, the direction would be perpendicular away from the surface. So at right angles or perpendicular away from the surface, that's electric field, just outside the surface of this conductor. Now, that's only valid for being very close to the conductor. If we go far away, where the shape of the conductor is relatively small to the distance that we're away from the conductor, then of course this becomes more or less a point object, and then the equation becomes quite different. But for something where you're very close to the surface, that would be the appropriate way in which we can find the electric field very close to the conductor. So basically, if you want to think of this in general terms, so if we take this equation right here, and take it this is the area, so maybe I want to go ahead and take this equation, we could then just simply state that the electric field just outside a conductor is equal to the Q inside your Gaussian surface divided by epsilon sub naught divided by the area that's perpendicular to the surface from your Gaussian surface. And that's how you would find the electric field strength just outside a charged conductor surface.